let's look at graphing stuff, polar stuff in Desmos. Let's start by just saying r equals theta. Now to type a theta in Desmos, what you do is type the letters T-H-E-T, and then when you hit the A, it will turn it into the Greek letter theta. So we get that nice spiral, kind of interesting. And it tells you what range of theta values it's using there. We can zoom out a bit and see how far out that takes us. Kind of feels like we're getting hypnotized. Then another thing you might notice is that the grid here is still in rectangular coordinates, but sometimes it's nice to see polar curves in polar coordinates. So if you go up to the wrench in the upper right here, graph settings, first we can turn it to projector mode, and then for grid, there's a rectangular grid and a polar grid. So let's click that, and then click over here to be done. So now we can see we've got, instead of x and y grid lines, we have r and theta grid lines. So an x grid line, like a vertical line, is now a theta grid line, a ray out from the origin, and it's got various helpful angles marked there. And a y grid line, like y equals 5, is now a circle. So that's an interesting way to think of polar coordinates as a different kind of grid on the plane. The way I typed this here, r equals theta, it'll plot it for you, but a better way to do it is to define a function, and using anything other than little r, so capital R is a good idea, to say r of theta equals theta, the same way you would say f of x equals x squared or something. Now it's plotting that as a 45-degree line. It's plotting that by default as a rectangular thing rather than a polar thing. So I don't want that. What I do want to do is say little r of theta equals big R of theta. And I get the same curve as before, but now I have this function that has its own name, and I can do things like take the derivative or work it into an integral if I need to. So it gives me more flexibility. Let's take a look at this curve. I've got a little animation set up here where t is my theta value, and I can slide that. And I've got a little line here pointing in the direction of whatever my current theta value is. So if theta is almost pi, then I'm almost over here at pi radians. And then it's showing the dot according to my capital R function. So we've got, as I add more and more to theta, now if I look here, I already had a direction, a point plotted at the direction going this way back when theta was much smaller, like there. And now that I've increased theta a full turn, I'm back at that same direction, but I have a larger radius value. So I can get more than one point along the same direction, but it's not the same theta value. This new value is the old theta value plus 2 pi. So thinking about is r a function of theta here, it can be a function of theta without being a function of the grid line you're on, the ray from the origin, because there's more than one way to be on a particular ray out from the origin. The original theta, theta plus 2 pi, theta plus 4 pi, etc. Let's try another function that I had mentioned. How about 1 plus 0.9 sine of theta? Actually, let's try minus. So what shape is that? That is a cardioid, just like we said previously, except this time it's actually kind of right side up from the Valentine's heart point of view. And let's trace out what's happening. So if I start out with theta of 0, so pointing directly to the right on the x-axis, I'm there. And then as I increase theta, I'm getting smaller r values and then bigger r values again. And I swing around here, and then what happens when I push theta past 2 pi? Well, the sine is periodic in theta, so all the values past 2 pi just act as if they're between 0 and 2 pi. So I just end up tracing out that curve again. By the way, this little green stick here and this point, It takes a little bit of magic to do that. You have to think back in rectangular coordinates. Desmos doesn't have a nice way of plotting a point in polar coordinates without converting it to rectangular, and we'll talk about that in a different video. So don't worry about what's going on there. You don't have to do that as part of the homework. It's fun to change this coefficient a little bit. Let's make it up to like 1.6. Then what's happening? Now the sine wave has an amplitude bigger than 1, so for some values of theta, we're doing 1 minus something bigger than 1, we get a negative answer. So if I start us back here at theta equals 0, we got that, that's reasonable. But now theta is pointing this way up and to the right, but then we have a negative radius. We can actually say what's big R at t. Our radius is negative right now, so even though theta is pointing us that way, we're actually going back the other way a little bit. And then we can continue on over here, same basic idea. And now my radius value is positive again, so I sweep around there. Let's try another curve. Let's try natural log of theta and see what happens there. So that's interesting, huh? We seem to be getting a spiral. But since log increases more and more slowly as theta increases, the amount of increase in radius each time is getting less and less. But it will eventually get out to infinity, right? Because log gets out to infinity eventually. Can we explain this little pigtail thing here? Let's bring theta back over here. So when theta is 1.4, for example, we seem to be getting reasonable results. I know I can't use negative thetas here, I just need a little more resolution. But once theta gets below 1, the radius gets negative, because log of things below 1 are negative, is negative. And so what's happening here with this pigtail, we're using theta values less than 1, and the log is negative, and we end up scooting out that way. Another fun quick thing to do is to use just a plain sine wave, but, not wave in this case, but put a multiplier on theta and see what we get. So that's just plain sine, but if I increase the frequency, I get all kinds of interesting shapes here. These are all generically called polar roses. Let's get a little more resolution. There we go. So if I set this to be integer steps, then I get some nice stuff. I just get a circle, but notice it's not the unit circle. And then I get something that has 4 petals, and then 3 petals, and then 6 petals, and then 5 petals. So that's an interesting pattern. So we can play with this and see that the radius is going negative kind of on every other petal, and sometimes it's lining up with previous petals. And then if we switch it to not integers, but we'll take theta up to 12 pi again. What do we get there? All kinds of interesting shapes. So that's the beauty of mathematics right there.